So first, I would like to thank myself for inviting me. So, as you may know, I'm replacing Anne Santenac, who unfortunately was not able to come because her boat was cancelled due to the weather. But fortunately, I have some slides I was able to recycle because I was invited a few weeks back in Nicolas Trepp's lab. So thank you. But because he did not show up to my talk, it will be new for him too. So don't feel too bad for him. So the fancy name-dropping title of my talk is Harnessing Disorder and Symmetries in Multimode Fiber, which of course doesn't mean anything. So a more honest will be, yeah, I want to talk about two seemingly random topics. So first, the effect of disorder in multimode fiber, and also the rotational memory effect. But I promise you there is some kind of link, kind of. So I was very lucky to work with very nice people, and also with Arthur Gucci on this topic. So Yaron is also from Israel at the same institute with Ori, and he was not able to join us because he wanted to stay with family, so that's too bad. And Rodrigo also had a poster on a totally different topic that he really carried out by himself. And if you happen to be in the committee of section 5 of CNRS, just give him a job. I mean, it will be very wasted if he has to go in a private company. So, my talk. So I come from scattering media, and I moved to multimode fibers. So a lot of people told me that it's the same because it produces a speckle, but actually it's not very true. There's things that are similar, things that are not. So I will spend a bit of time trying to explain the differences and what is common. And then, because I only know how to do one thing, I try to measure the transmission matrix in multimode fibers. And I will also tell you that, again, it's a bit different from scattering media, and you have to choose the basis carefully if you want to study the physics. So I will tell you why we want to measure the transmission matrix in the mode basis and how we can do so. And then, once we have this tool, I will show you how we can use it to study the effect of disorder, and also to study and use what we call the rotational memory effect in multimode fiber that was observed first by Alan Mosk and Luba, I think it's the way to pronounce it. And yeah. So, scattering media versus multimode fiber. One thing that is very different, and that was very disturbing to me in the first place, is that when you eliminate either one of them with coherent light, you end up with a speckle pattern. So you focus light at the input of a scattering medium, you have a speckle pattern. You do the same with a multimode fiber, and you have a speckle pattern. But it's still very different. And the reason is that in free space, when you have a scattering medium, the very fact that you have a speckle pattern is a signature of a spatial disorder, which is not the case for multimode fibers. Because even if the fiber is perfect, if you focus light at the input of the fiber, you do have a speckle pattern at the output. You do have a speckle pattern because you have dispersion. This is not a mode of the fiber. So when you focus light, you excite a lot of different modes with a given phase. And then these modes will propagate with different speed, so they will accumulate a different phase. And because the length of the fiber is very long compared to the wavelength, at some point it looks random. So it's like you do the combination of the same mode you excite, but with a random phase. So that makes things a bit different, because when you have a speckle pattern, you don't know if you have disorder or not. And also, disorder can also contribute to the speckle pattern too, if you have some random mode coupling, for example. But you need to be able to discriminate between these two effects. And a question I had a lot, actually, is why do you want to study multimode fiber? The Russians did it everything in the 70s. Yes and no. So first, I mean, the easy case is when you have absolutely no disorder in the fiber. You can find the solution, you can find the modes analytically or semi-analytically, because sometimes it's not really easy to solve. So we have all the predictions we want. Then the thing that was studied next is what you have when you have very, very strong disorder. What I call a strong coupling regime is when all the modes are statistically explored when I excite one mode in input. And in this case, there was a lot of things that were studied, and mostly statistical predictions. But there is some problems with that. I mean, nowadays it was very nice, but compared to what we can do and what we want to do nowadays, there's something that are missing. First, it's statistical predictions. So we don't know what to do when we have one realization of disorder. And another thing is that this regime doesn't exist. It doesn't exist in fibers just because if you couple all the modes, that also means that you couple propagating modes to non-propagating modes. So that means light going out of the fiber. So before you reach this regime, you have no energy left in the fiber. So everything happened in the transition between these two regimes. And this intermediate regime was very little explored. Okay, so like I told you, I know how to do only one thing. So I measure transmission matrix for scattering media. So now I want to measure transmission matrix for multimode fibers. And people did it before me. And the very seminal paper in this field is the one by in the group of Thomas Sismar. And I want to do the same thing. So I want to measure the transmission matrix because it links for one given wavelength everything that happened in input to everything that happened at the output. The problem is we show that we have a spectral pattern, whatever we do, even if there's no disorder. So in this paper, they measure first the transmission matrix in the pixel basis, and this is what you get. So I don't know if you can tell me from this if there is disorder or not, but it's very difficult because, like I said, we still have a spectral pattern. And actually, this is a matrix that comes from a 1 centimeter fiber and a straight fiber. So if you project it in the mode basis of the fiber, you have an almost perfect diagonal. So there's no disorder in the fiber. So yes, we want to measure the transmission matrix, but if we want to study the physics, we have to do it in the mode basis. Just very quickly, because I had a lot of questions about that. So what does the mode look like in a multimode fiber? So we're working basically with a waveguide, but a waveguide with this very, very small numerical aperture. So in this case, it's a scalar problem because you can decouple the two polarizations. So you can solve the system for one polarization, and you will have the same thing for the other polarization too. And the mode usually look like that. You have the propagation constant. So Z is the axis of the fiber. And if you look on one plane orthogonal of the fiber, what you see is it's parameterized by two values, L and M. M is the orbital angular momentum. So it's a number of 2 pi you have around when you go around the cycle. And L is the number of oscillation in the radial direction. So for example, this is L equal 1. This is the fundamental mode. And here you see that you have 3 oscillations in the radial direction. So this is L equal 2, M equals 0 because you have no orbital angular momentum. So this is the mode we are dealing with. And depending on the fiber, they look mathematically they're a bit different, but they look the same. So you basically have the same structure. And the two main kind of fibers, there's a lot of fibers, but the two main kind of fibers are step index. So you just change the index in the core, or gradient index fiber. It's basically almost a parabola that is cut. And outside we call it the cladding, and inside is the core. And these two fibers are a bit different. And for the same core size, so this is the dispersion relation for these two types of fibers. And in the step index case, you see that you have little degeneracy, and it's linear. This is the propagation constant, and this is just the mode number. And the only degeneracy you have is between the two opposite orbital angular momentum. Of course, if there's nothing else in the fiber, because if the fiber is perfect, going one way or the other way is the same. And in the case of a gradient index fiber, you see you have groups of almost degenerate modes. And they are degenerate when you have L plus 2M equal constant. So you have groups of degenerate mode or quasi-degenerate mode, because you see that they are not quite degenerate in the end, that the size grows when the number of modes increases. And you also see that the total number of modes isn't the same. It's approximately half. Okay. So now we know that we want to measure the matrix in the mode basis. So the first idea is to do that directly, meaning that we have, So in this paper, for example, done in the group of Joel Carpenter in Australia, what they did is they use a SLM input and a SLM in output. They modulate the two polarization, and what they did in input is they exactly send, or try to exactly send one mode. They measure the projection on another mode, and so on. So first, the drawback of this technique is that if you have n mode, you need to n square measurements, because you measure one element at a time of the transmission matrix. But that's not the most important thing to me, is that you need to be very carefully aligned if you want to do that. Because if you do not send exactly what you think you're sending, meaning a mode, then you will screw up the transmission matrix. And I would come back on why this is difficult in the other way to measure it. And the other way to measure it is say, okay, I measure the matrix in the pixel basis, because I know how to do that. And then, numerically, once I have this matrix, in the pixel basis, I can, because I know the mode, I can compute the mode, like I said. The mode of the perfect fiber is something quite easy to have access to. So I can always project with a change of basis matrix and get the matrix into mode basis. So this is trivial mathematically. But that's not so easy, actually, because you need to be very carefully aligned, and you need to know perfectly your system, because you are very sensitive to aberrations, you are very sensitive to misalignments, and also to uncertainties you have about the fiber parameters. But the most important thing are misalignment and aberration, because when you're measuring in the pixel basis in free space, I mean, it's just a translation if you don't have the right center, for example. But here, if you don't have the right center of your fiber, if you send a mode, but it's a bit of axis, it will change a lot. It will project on a lot of other modes. So it will be very difficult to interpret the matrix. So it looks very easy. It looks very trivial mathematically, but it's very, very difficult. And I think the best proof is that when you measure the transmission matrix, you have all the information about the system. So it sounds like a very perfect idea to study multimode fibers, but very few people did it, because it's very sensitive and it's very difficult. And to show you, this is a setup that was used to measure the matrix I showed you before. I don't want to do that. I mean, that's very scary. So, and even with that, actually, what they observed was not the matrix I showed you. What they measured was this, not a diagonal matrix. Because with what I think is weeks of alignments, it was still not perfect, not good enough to have the good matrix. And what they did, a very nice idea, is to iterate over the possible degrees of freedom you have, so defocus, misalignment, and so on. So they had something like 12 degrees of freedom, 16 input and 16 output, so misalignment in the 3 directions and also in the 3 angles direction. It took 5 hours to iterate, and they get this diagonal. But one of the problems with this technique, which works, is that they optimize the diagonal. So that works very well if you have a matrix that is a diagonal, meaning that you have no disorder or no mode coupling. But what we want to do is to study disorder. So if we have intrinsically in the fiber some mode coupling, this will not work. So we can and should measure the matrix in the mode basis, but it's very difficult. And what we want to do is to do what they did, but doing much faster and without the need to align a lot of things. And once we have this, we can study a lot of fibers, because one of the challenges is if you want to use that, for example, for telecommunication, you want to be able to measure the matrix of a fiber, whether it is for characterization in the workshop or if it's directly in production. You don't want to spend 3 weeks aligning every time you change a fiber. So the requirements are we want to go fast. We want to relax constraint on our experimental setup with the sensitivity to alignment and aberration, and also on the hypothesis we make about the fiber, the low coupling regime when we do the post-processing. So to do that, we will rely on two tools, DMDs and deep learning framework. And as you've seen today with Allard and Ori, there is smart ways to use deep learning framework in optics. And usually, the smart way is not using out of the box the tools they give you. And I want to spend just a few seconds on that, because when the bubble of deep learning arrived in this community, people rushed to be the first one to apply deep learning in scattering media. But they use the tools that were available. So for example, convolutional networks. But it didn't work very well at the beginning. The reason that we don't have the same hypothesis. So it's not agnostic at all. And for example, convolutional neural network, they use the fact that the information is local, at different scale maybe, but local, so because it looks at patterns. But when you're working with speckled patterns, it's totally delocalized, so it's not efficient. And another thing I want to say about deep learning is, fundamentally, deep learning is very inefficient. It's very inefficient, but it works very well when we have no other tool. So basically, when we have no information, or when we don't have the underlying model, for example, we don't know the equation in your brain that make you recognize a cat to a dog. In this case, it will work because you replace the fact that you don't have the formula by a huge number of degrees of freedom with a huge data set to feed in the algorithm. But if we do that with physics, that means that we throw out in the bin all the physical insight we have about our system. So the smart way is to include physics into the architecture or the cost function of the network. Okay, so DMDs, what is a DMD? DMD are micromirror devices, so that's exactly what is powering this projector here. It's a matrix of small mirrors that goes very fast. So why I want to use that? So first, liquid crystal, that is the most used device to do wavefront shaping because it allows a pure phase modulation. It has a good diffraction efficiency, low aberrations, but a very poor refresh rate, about 10 Hz. So we went to these DMDs. They are fast, more than 10 kHz. They are cheap. Well, the chip itself is cheap. But if you want to make it work in research, the electronics will be dedicated to research. So you will pay $10 for the chip and 15K for the electronic board. But okay. But it has a diffraction efficiency that is okay. But the main problem is that it's amplitude modulation only. And actually, it's more than that. It's on-off, because it can just move the beam in two directions. So if you're looking at one direction, it would be either on or off. And also, it has a lot of aberration. That's something we discovered, and it's not detailed anywhere, for the good reason that in this projector, for example, the plane of the modulator is conjugated with this screen. So the fact that you have aberration because the modulator is not perfectly flat, you don't see it. Because in this plane, it will be only phase. So in our case, we do see it a lot. So there is some tricks, but don't worry, it's possible. And very quickly, I want to tell you that the fact that we cannot modulate directly the phase is not so much an issue, because we can actually lose a bit of resolution in order to get amplitude and phase modulation. And that's perfect for fibers, because we don't have a huge number of modes. So that's okay if we lose a bit of resolution. And for example, well, yeah, first, the basic principle is you instead of displaying directly what you want, you display grating on your modulator. So on my SLM here, which is a DMD, I just put a grating. And I'm taking only the first one order. So let's say you have a grating with a period of 4 pixels. You put 25% of the energy here. Let's say that now you have the same grating, but you moved it by 1 pixel. It's still the same spatial frequency. So you have the same energy, the same spatial shape here, but you change the global phase. So that means that by adding a fringe to your image, and by shifting spatially the fringe, you can translate this spatial phase into optical phase. It's a bit more complicated, but the basic idea is here. So let's say that I want this pattern with hexagons, and I want low amplitude that is increasing when I go in the outer ring. And I also want to rotate the phase with the azimuthal coordinates. And this is what I will print on the DMD. You see that I have some fringes in one direction that allows me to modulate the phase. And to modulate the amplitude, I just remove some lines in the orthogonal direction. This way, I can use two directions, one to modulate the phase, the other one to modulate the amplitude. And if I do that, this is what I would get experimentally. So this is simulation, but that's very, very close to what we get experimentally. I get this field, this is the phase, this is the amplitude, and if I project on the hexagon that I had before, I almost get exactly what I wanted to do. So again, I lose a lot of resolution because each of these hexagons are composed of many pixels. But because again, I use multimode fibers, it's quite okay. And if you want to know the trick that we use for this kind of thing, we have everything on the website, a lot of tutorials or codes and everything. Now let's measure the matrix. And again, no effort, not too much effort, in measuring, in aligning everything. So we want to measure the matrix in the pixel basis and then to project it in the mode basis. But now we know that the matrix we need to project is not only the shape of the ideal modes, we also have aberration, misalignment to take into account to have the right matrix in the mode basis. And this is what we measured initially. So we just projected into the mode basis, and this is what we get. Because, again, we didn't take care about the misalignment and aberration and so on. So, how to learn that? And like I said, I think that one of the best ways to use deep learning framework is to include the physics inside these networks. So, I start with MI or MO is the input or output change of basis matrix. So basically, that's the shape of the modes. So ideally, if it was perfectly aligned, I would just need to use this matrix. And then what I do is I add some layers that correspond to a misalignment or an aberration. So the first one is the translation. I allow my system to move to compensate for the misalignment. I also add some Zernike polynomial in the phase. So they will basically mimic the effect of aberration. And for each layer, it's differentiable. So we can use a toolbox, the autograd, and so on. And also, there's only one parameter per layer. So we don't have a huge number. I mean, the space of solution is not huge because we restrain it knowing the physics. So there's only one parameter per Zernike polynomial. Then we do a Fourier transform, and we also add Zernike polynomials in the Fourier plane. So we allow ourselves to correct for aberration in 2 different planes. And then the only thing we need to use frameworks is a cost function. And it's quite, actually, it's kind of easy because we have a fiber that is a waveguide. So we know that if we do everything correctly, all the energy in the pixel basis has to be in the mode basis because by definition, all the energy goes through the modes. But because, in general, when we project into the mode basis, we reduce the dimension, if we don't have the right projection, we will lose some energy. So we simply project our matrix in the mode basis, and we try to maximize the norm of that. Because again, the best thing we can have, the maximum, is when we have the same energy in the mode basis and in the pixel basis. And that's what we should have if things are corrected. So we do that, and it takes only a few seconds to optimize. And this is what we get in the end. So it's not as diagonal as the one before, because it was a 25 centimeter fiber, not 1 centimeter. But you see that almost all the energy is in the diagonal, and even when you have coupling, it's mostly between the degenerate groups of modes. And 95% of the energy is conserved, so we are quite happy. And because we don't have too much effort on the alignment, Maxime and then Rodrigo, who continued this experiment, was able to change the fiber in 2 minutes. So a few seconds. Yes, sure, Dave.
So there's one other degree of freedom that is difficult to deal with in my experience is the diameter of the core. Is there a way to what do you do to find the diameter of the core? Can you put that into the fashion profile?
Yeah, that's tricky. There are multiple ways to deal with it. So first, if you put a defocus in the Fourier plane, actually, you will also enlarge your system. So there's one way to do it. The problem is doing a transformation of the grid is not very easy in these frameworks because it's kind of difficult to be differentiable. And there's no interpolation. So meaning that if you are in between 2 pixels, you will have a step, and they don't like that. So what we do is, because it's only 2 degrees of freedom, scaling in X and scaling in Y, we do an optimization before running this one. But actually, we're actually working on a way to find all the parameters of the fiber, including the index profile, in a differentiable way. So again, if you want the tools, we share everything. And do not hesitate to harass Rodrigo if you want some information. So now, finally, let's study disorder in the fiber. So we start with the easiest disorder we can find. So we just press at one point on the fiber. And we measure the matrix for all the possible deformation we induce in the fiber. So first, no deformation, we have a diagonal matrix. We press on the fiber and we start populating the off-diagonal elements, which means we introduce mode coupling. And now we want, in a way that is kind of similar to what Alexander is doing in OCT, is we want to quantify what is the deformation compared to the ideal case. So we define this deformable operator that is the mode for a given deformation, the mode basis transmission matrix for a given deformation, multiplied by the inverse when there is no deformation, minus identity. So we build it so that if the matrix is not modified, it's equal to 0. And then we study this operator. And what is very funny is that if we do a PCA, principal component analysis, we can show that for every possible deformation, we can, even though the operator itself is modified, actually it has only few degrees of freedom, meaning that we have a very good approximation of this operator just by building it with two fixed operators, and two fitting parameters. So for any deformation J, I can find alpha and beta so that this deformation operator is approximately equal to alpha U1 plus beta U2. And physically, what does that mean? So let's look at U1 and U2. So U1 is basically a diagonal matrix. So what does that mean? Diagonal, actually, you have a negative coefficient for this one. That means that we remove energy from the ballistic photons. So in the case of multimode fibers, the ballistic photons are the photons that stay in the same mode. And the fact that we have this diagonal matrix, it just reflects the fact that we remove energy from the ballistic photons. So it's, this is an analogy with scattering. And the second term is this operator. So here, the problem with the representation of the mode basis in the multimode fiber is how you sort the modes. So here, I was very stupidly sorting that by minimum and maximum propagation constant. But if you sort them by orbital angular momentum, you see that you have this shape, and it's enlarged in the middle just because you have more radial modes in the middle. But basically, that means that the second effect that happens is you couple to neighboring modes. So it's like single scattering in the analogy. So that just means that in the K space or in the momentum space, you have single scattering. It is impacted once by the deformation, which makes sense because we press only once in the fiber. And another thing we wanted to study is that possible to avoid the disorder? So it can be interesting in telecommunication. And when, for example, you have fibers just beneath the road, so there will be some modification. And here, the modification is just what we did before, pressing on the fiber. And we know from a lot of physics before, but it was applied in optics recently, and especially in the group of Stefan Rother, that we can define a general Wigner-Smith operator. So when you have a given operator, a transmission operator, here it's H, our transmission matrix, you can build this operator that you see here that you have the inverse of the matrix, and here you have the derivative of the matrix with respect to the parameter that you would change. And if you do that, the eigenmodes of this operator are insensitive to the first order of this parameter. That's exactly what we want. So this figure is very difficult to understand, so let's try. What we do is we press a bit on the fiber, this is a deformation, and around this point, we estimate the derivative of our matrix, and then we compute the Wigner-Smith operator. And then what we do is we send modes at the input of the fiber, and we measure how they change when we press on the fiber. So for example, if we send a random input, so this is the blue curve, this is what I get as the output for no deformation, and this is what I get at the output for a lot of deformation. So it's always the output, but this is for a different value of the deformation. I do not change input. I press on the fiber, I see how the output is modified. And if we look at the correlation, so we compute the maximum correlation, I mean, we compute the correlation with respect to the value we computed the derivative around, and we see that it does decorrelate a lot. But it's not very honest to do that, because we all know that, we now know that not all the modes are affected the same way by the disorder, because, for example, the fundamental modes are more confined. So because the disorder always appear at the edge of the fiber, they will be more protected. And if I send the fundamental mode, this is what I get in green here. It's still modified. So it's confined, but it's still modified. And you see that the correlation goes down to 75% maybe. Now we compute the eigenmodes of our Wigner-Smith operator, and this is all the red to brown curves. And it does look random at the output, but it's not modified. And only 4 of them do worse than the fundamental modes, but we also have 4 modes that are close to the cutoff. So basically, they are not really propagating anyway. So we have a full basis of modes that are not affected a lot by disorder. So that's a question you also had. Does it translate to another deformation? I don't know. But it's still interesting because, again, if you have a fiber that goes beneath the road, when you have a truck, when you have a car, when you have a pedestrian, you basically have the same deformation, but with a different level of disorder, different strengths. So it can still be interesting. So yeah, on this part, I can thank my collaborators. And if you have some question here, you can, no, I can move. So now I want to talk quite quickly about the rotational memory effect. So that's very nice because a lot of talk about memory effects. So now you know that when you send a plane wave, when you send a plane wave on a scattering medium and you move the angle up to a given angle, that is the range of the memory effect, you will have the same speckle pattern but just shifted. So it will be highly correlated in the range of the memory effect. And you have kind of similar effect that was first measured by Allard and Yuba, and that was also studied in this paper by Dave Phillips and Thomas Sismar, in which they observe this memory effect. When you think about it, it's quite trivial because if you have a perfect fiber, you have a perfect cylindrical symmetry. So if you rotate the input, you should rotate the output exactly the same way. But the problem is fibers are not perfect. So this is actually the formalism that was explained in this paper by Dave, which is very nice because that's exactly the way we should see it, meaning that having a memory effect, meaning that you have a transformation that commutes with the transmission matrix. What does that mean? If it commutes, meaning that you can have, let's call our operator, transformation operator O. If you have HO that is equal to OH, that means that applying the transformation before or after is exactly the same, which is exactly what is a memory effect. So very nice paper, very misleading title, but very nice paper. So this is a perfect memory effect. But in real life, you don't have a perfect memory effect. That's exactly what we said. In the case of scattering media, if you rotate the input up to a given angle, you have approximately the same speckle pattern, just shifted. If you move it too much, then it decorrelates. Oh, that's linked to the fact that the transmission matrix is large, have a given length in the diagonal, but I want to skip that part because I don't want to spend too much time on that. So in the ideal straight fiber, the rotational operator, when we rotate around the center of the fiber, should commute with the transmission matrix. But once again, it's something that is very, very sensitive to aberration and misalignment. Because having a memory effect that is not perfect, that means that you basically break the cylindrical symmetry. But if you do, again, misalignments, if you are not perfectly on center, you do break this symmetry. So basically, you will not know if the fact that you break the symmetry comes from your mistakes or it comes from the fiber. And this is what was measured by Allard, and that's a pretty big deal, because I tried to do that for a long time after it was published, and I was never able to reproduce these measurements, because you need to be very, very perfectly aligned. And I was discussing with Ori about that, who told me exactly the same thing. But then we thought that that's a bit stupid what we're doing, because I just spent 30 minutes bothering you with the way we were able to compensate for aberration, so we can do that too here. So this way we can remove the effect from aberration and only measure the effect of the fiber. So can you trust me that we can remove? Okay. You don't? Okay. I cannot be trusted, but I will show you. So again, we measure the transmission matrix. We present the fiber, is just to see if we do destroy the memory effect. But first, we need to measure it. And this is what we get. This is actually experimental data. I was very amazed when Rodrigo showed me this curve, because it looks so smooth. So this is the rotation with respect to the rotation, the correlation with respect to the correlation angle on our fiber when we press on the fiber. So here is we increase the deformation. And the way to do it is, because we're able with our deep learning framework to know what are the correlation on misalignment and input and output, instead of rotating the mask in the plane of the DMD, of the modulator, because we know the aberration between the plane of the modulator and the plane of the input, well, we send something in input in order to have a perfect rotation in the plane of the input fiber. Input facet of the fiber, sorry. So we rotate in this plane, we measure the output field, we compute the correlation, and then we increase the correlation and we repeat, and we have this shape. One thing that is interesting is you see that you have a peak at pi. So the correlation comes back. And that was also observed by Alan Mosk, and it's kind of difficult to, physically know where it comes from. And another way to illustrate this effect is we can learn how to focus on one point and then rotate the input wavefronts. And then we do see that we rotate the output focal spots, but it gets degraded when we press too much on the fiber. So now we need to know, to have a good model for the deformation, to know exactly where it comes from. So it looks a bit complicated to me because I'm not a theoretician, but hopefully Arthur did all the calculation for me. So let's add a deformation to the index profile. And we can characterize the disorder by a few parameters. First, in the z direction, we just assume that we have a given correlation length, meaning that we can divide our fiber into segments of this size, and they decorrelate these segments. And that's something that can be measured by our collaborators in the industry, so they know what these parameters is. Then we need to assume that we also have some radial disorder. The way it's very complicated, and there's a lot of different techniques to actually build the fibers, but the index profile is never perfect. For example, there's almost always a small dip at the center of the fiber. And we can reasonably assume that the error will be proportional to the difference between two layers. So we put some dopant in the glass at a given layer size, and we build layers by layers. So we can assume that the error will be proportional to the derivative of the index profile, and also proportional to the layer size. And then the fiber is not perfectly cylindrical. So we know that, because otherwise we'll have a perfect memory effect. So we just add some cosine in the azimuthal direction in order to add this kind of deformation. And that's the parameters we want to characterize. So we want a model for which, if you give me these values, I can have the correlation, or the other way around. So the correlation looks like this. Okay. You have to believe after that. And that's basically two important things, is that you will couple the modes better if, of course, they have a close-by propagation constant. It's like energy when you do typical mode coupling theory. But also you have an effect of the symmetry of the modes. And that's something that was never studied before, because the effect of the symmetry of the mode, it's an interplay between the symmetry of the modes and the symmetry of the deformation. So for example, if you have a deformation with a given number of lobes in the deformation, you will couple preferentially some modes. And that's actually one of the big parts of what's happening here. So we measure the curve experimentally. So this is the blue curve for no additional deformation. So all the defects or the error, the randomness come from what come from the fabrication of the fiber. It's intrinsically in the fiber. And we have this blue curve. Then, because we have this formula, we fit it with the gamma. We fit the gamma values in order to fit the curve. So then, if you are following, you say, okay, but that's stupid because I'm fitting a periodic curve with cosine function, so it will always work. Yes, that's true. So now we wanted to see if the values we found were physical or not, and then we simulate with the value we found of the gamma parameters, we simulate without any additional fitting parameter what we will have in this situation. So we plug this disorder in our computer, and what we get is the red curve. So the black curve is theory, and the red curve is simulation. So the fact that without additional parameter we do have the same curve means that, well, I guess it's not just luck. And then when we press on the fiber, we see that we destroy the memory effect. But another thing that is important is that when we find this gamma value, that means that we are able, with a macroscopic measurement, to know what is the deformation, the microscopic deformation due to the fabrication process. Because the way they usually characterize the index profile is in the preform. The preform is a large cylinder of glass, and then they draw it and they eat it, and then you get kilometers or tens of kilometers of fiber with one cylinder. So they usually characterize the index profile before they draw it. But this deformation comes from mostly when you draw, when you build a fiber. So you will need to break the fiber and to have a microscope in order to estimate the index profile. But here we are able to do it from input to output measurements and without too much difficulties. And if you don't have the problem of the aberration, you can even do that with just intensity measurement by rotating the input pattern. And another thing is that you can say, okay, but you just do it once, and basically if you do the same fabrication process, it should be the same. And here it's a different spool of the exact same fiber, so the same serial number. And you see that before that I had something smooth here, and now I have another peak at pi/2 and 3π/2 for the same fiber. I mean, different spool, same fiber. That means that we have another parameter, which is gamma 4, that is more important for this fiber than for the other one, meaning that if you draw the same fiber multiple times, you will not have the same disorder. So that's very interesting for people building fibers to know this, because what they try to do also is they try to minimize the coupling between the mode, and because they don't know what is the structure of the deformation inside the fiber, they assume that it's a white noise. And you see that it's not white noise, because there is a very important effect of the deformation with respect to the symmetries of the modes. So that also allows to improve their models. Okay, so just to sum up this part, to measure the rotational memory effect, we only need access to input and output. It's possible to do it just intensity measurement as long as you know the aberrations of your system. So it's purely microscopic, but it does give access to microscopic parameters of the fiber. So it can be useful for telecommunication application, but it can also be useful for imaging. I think I have a few slides for imaging, and I think it would be, I have 5 minutes left, something like that? 6, good, perfect. So we've seen in multiple talks that we can use the memory effect to do some imaging. And it works very well in scattering media, as long as the range of the memory effect is large enough, because you have some assumptions that are always good in scattering media. So I will go very fast on the detail because it was done before, but one strong assumption that you need is that in the case of the angular memory effect, you need two things. You need to be able to know that even though you don't know what the speckle pattern looks like, you're able to shift it, so it will be the same. But that's not the only assumption you need. You also need to know that the autocorrelation of the speckle is close to a Dirac function. Because otherwise, basically, if you try to do the reconstruction of the image, basically, you will not be able to differentiate the structure of the illumination pattern to the structure of the image. And the fact that you have something that is random, it guarantees that it will work. So you need a good range of the memory effect. So ideally, if we want to use the rotational memory effect for imaging, first we need to know that the correlation is always high, but you see that it does decorrelate to 75%, so it's not perfect in our case. And you also need to have something that is with a small correlation width, autocorrelation width. But in our case, it's not the position, it's theta. So of course, we only have information about theta in this case because we have no straightforward memory effects in the radial direction yet. So you see, correlation, in this case, it goes down to 65%. So the range of the memory effect, if you say something like, just randomly you want 80%, the range is very small. So you will not be able to recover an image over all the angles. So that's not good. So can we do better? Basically, for one given realization of disorder, this is averaged. And this is the error bars in grayish. And can we find channels, input modes, for which, or input channels, for which the correlation is better? So I'll go quickly, but we can define an operator for which that represents the correlation, meaning that when we project it an input and output on a given wavefront, that gives us a correlation. So what is good is when we have an operator, a linear operator, we can just find its singular values, because the singular values will be sorted, and the first one will be the one that gives the better value. And because this operator represents the correlation, it will increase the correlation, at least for a given angle. So for example, this is what we do. And I always plot, so we don't see it much, but in gray you have the average value that goes down almost to 60%. And these two blue curves are the first one and the second one. And I will tell you why I'm not only interested in the first one. And the first one is quite flat, so it looks like very good. And the second one has a peak with a good correlation only at the value we want. If we try to, so here, the angle we try to maximize the correlation was pi over 4, and pi over 2 is 3 pi over 2. But the problem, and if you want to maximize over the whole range, we can always do the sum of this operator for example, 8 values. And this is what we get. So the best one is the black solid line. And the second one, it's still very good. It's the dashed line. And it stays almost always over 90%. So again, why I do not show you only the first one, but because it looks perfect. But actually, the first one is the fundamental mode, which is useless. Because if you rotate it, you have the same thing. So you don't get any information. But also mean that the autocorrelation is flat. So that's the assumption that we had with speckle pattern that we do not have here, because there is some structure. So the fact that if you rotate it, you have the same information, meaning that it means that you cannot use it to do imaging. But the second one is speckly. So the second one, it has a correlation that stays roughly over 87%, and it still have a good autocorrelation function. So ideally, we may use it for imaging. So that's the next step, because again, that only gives you access to the azimuthal information, because there's no radial direction. It's like if you have the angular memory effect, but only in the x direction and not in the y direction. You only have half the information. We have half the information, but we do have some information, so it's not nothing. And yeah, maybe we'll be able to use that for something practical. It's not the case yet. Thank you.